Hi, today we will be moving on to Module 3 of our CSEC Chemistry exam review. And I just wanted to remind you of this motto for extra time tutoring, which says that the human mind, once stretched by a new idea, never regains its original dimensions. So first we will look at our objective, which asks us to distinguish between pure substances and mixtures. We are to consider elements, compounds, molecules, their compositions, their properties, etc. So first, matter is separated into substances which are pure and those which are considered to be mixtures. A pure substance is made up of one type of particles. Examples of pure substances include elements and compounds. As you can see inside here for the element, it is made up of one type of atoms. As opposed to a compound has more than one type of atoms joined together by a chemical bond. However, we are still seeing one type of particle right throughout this substance. As opposed to pure substances or mixtures have two or more types of particles sharing the same space. Or mixtures can be further subdivided into those which are homogeneous and those which are heterogeneous. In the homogeneous mixture, we have more than two or more than one type of particle, two or more. So we have a type of particle here, which is a compound, because we can see that it has more than one type of atoms joined together. And then here we have another type of particle. So because we have more than one type of particle present in the same space, then it is a mixture. Also, the particles are not chemically joined. As you can see, there is no chemical link between this particle type and this particle type. However, the particles are evenly distributed throughout the mixture, and so it is considered to be homogeneous. On the other hand, a heterogeneous mixture also has two or more types of particles. Here we have a compound, here we have an element, and there are differences in how the particles are distributed. So essentially, at the top half of this space, we only have one type of particle. And then at the bottom half, we have a different type of particle. There is no uniformity in the distribution as we have seen in the homogeneous mixture. Again, this is showing us the difference between the heterogeneous mixture, which has more than one type of particle that is randomly they are randomly distributed, versus the homogeneous mixture that has more than one type of particles, but they are evenly distributed throughout. Next, we need to learn how to distinguish among solutions, suspensions, and colloids. We need to make reference to particle sizes, the passage of light, sedimentation. So solutions have the smallest type of particles which are suspended in a solvent. They are usually transparent even though they are colored. They don't have the Tyndall effect, meaning that they do not scatter light, so light will pass directly through a solution. They do not exhibit Brownian motion, and you cannot separate a solution by doing filtration. That's because the particles are small enough to pass through the pores of the filter paper. Colloids have larger particles than what you will find in a solution, and the colloidal mixtures can be translucent, meaning that they are not transparent. However, you can still see through the mixture, as you will see in the next slide. Sometimes they might be opaque. They do exhibit the Tyndall effect, meaning that light is scattered when you try to pass light through the colloidal mixture. They can exhibit Brownian motion, and like the solutions, you cannot separate them by filtration because the particles of a colloid are small enough to pass through the pores of the filter paper. Suspensions are often opaque, but they may appear translucent. That is, if the particles of the suspension have settled to the bottom. They have the largest particles of the three types of mixtures. They do not exhibit, well, the Tyndall effect is not applicable to them because they are usually cloudy, so no light is expected to pass through a suspension. The particles will separate if you leave it unsettled, or if you leave it undisturbed, and you can separate a suspension with filtration because the particles of a suspension are large enough to be blocked, and to be kept in the filter paper. They cannot pass through the pores of the filter paper. Here we have another table showing us the difference between the three types of mixtures. Solutions have the smallest particles, as you can see here, up to 10 to the minus 9 meter. If you left a solution to stand, the particles will not separate. They will remain suspended in the solution. They cannot be filtered because the particles will pass through the filter paper, and solutions are usually transparent, so you can read clearly. If you put a piece of paper with a word behind the solution, you can read it clearly. Colloids have larger particles, up to 10 to the minus 6 meters. Some colloids can separate out on standing if you leave them for several days or up to years. They can be separated if you had a semi-permeable membrane, but they are also not filterable. And they are translucent, meaning that it might not be transparent, but you can still be able to read the words that you place behind a colloid. As opposed to suspensions, which are usually murky or opaque, the particles are large enough to completely obliterate the words which are behind it. And the suspensions have the largest particle size, up to 10 to the minus 5 meters. And these are the ones that we tend to filter because the particles of the suspension will not pass through the pores of the filter paper. So here we have an example of a solution, a colloid, and a suspension. This objective asks us to identify different types of solutions. You are to appreciate that you have solid in liquid solutions, solid in gas, solid in solid, gas in liquid, liquid in liquid, gas in gas. So we're going to look at this table that gives us various examples. So remember, in a solution, you have a solute and you have a solvent. Now the solute can change from solid liquid to gas. The solvent can also change from solid liquid to gas. So a gas in gas solution, an example of that would be air. So we have oxygen as our solute dissolved in this solvent, which is nitrogen, but both of them are gases. And then we have liquid solution. So we can have a gas dispersed in a liquid, for example, soda, where we have carbon dioxide gas suspended in water, the liquid. Also, we can have a liquid in liquid mixture, for example, vinegar, where we have acetic acid dissolved in water. Both of them are liquids. And a solid in liquid mixture includes seawater, where we have sodium chloride, which is salt, dissolved in the solvent water. We also have solid solutions, for example, a liquid dissolved in a solvent, where a dental amalgam is an example, where mercury, which is a liquid metal, is dispersed into silver, which is a solid metal. And an example of a solid in a solid mixture would include metal alloys, for example, brass, where we have zinc dispersed in copper solid. Now we will discuss our separation techniques. So the objective asks us to apply suitable separation techniques based on differences in properties of the components of the mixtures. Properties to be include particle size, boiling point, crystalline structure, solubility, and solute mobility in the solvent. So here we have a summary of the various methods of separation. This apparatus is basically showing us simple distillation. This apparatus here can be used to show crystallization or evaporation. This one here represents fractional distillation. As you can see, the difference between the fractional distillation and the simple distillation is that this one has an additional apparatus, which is known as a fractionating column, and we do not see that in the simple distillation apparatus. Here we have a separating funnel. This shows us filtration. So let us look at the various separation techniques and see what property are we using to separate the various components. For example, in chromatography, what we are doing is that we have a solution with various compounds in it, and the compounds have similar properties, except that they have different polarities. So the only thing that we are using to separate the compounds when we're doing chromatography is that we are separating them based on their polarity. In filtration, we have solids, or we might have groups of solids dissolved in a liquid, and what we're using is the fact that the particles are large and so they can't pass through the filter paper, while the liquid solvent can pass through the filter paper. In evaporation, we're making use of the fact that we can cause the solvent to vaporize, and we will leave back the solute, which is usually a solid, and the solid should not decompose when we heat the mixture. In crystallization, we're making use of the fact that we have dissolved solids in solution, and these solids become less soluble as we cool the solution down. Simple distillation, we usually have two or more liquids that are mixed together in a solution, or we might have a solid dissolved in a liquid as a solution. In this case, however, when you have a liquid or when you have two liquids dissolved in a solution, we are separating them based on their differences in boiling point, and they usually should have large differences of over 50 degrees Celsius in their boiling points for us to use simple distillation. In fractional distillation, we usually have a mixture of liquids which are miscible, meaning the liquids are able to mix completely with each other. However, the only difference between the two liquids is that they have differences in their boiling points, but the differences are small. So the differences are less than 50 degrees Celsius, and that's why we need a fractional distillation versus simple distillation when the differences are large, over 50 degrees Celsius. When we use a separating funnel, that's when we have two or more liquids which are immiscible, meaning they do not dissolve in each other, usually because they have large differences in their polarity. Sublimation makes use of the fact that one of the substances in the mixture is able to sublime, meaning that when the mixture is heated, one of the substances will be able to be converted from a solid state to a gaseous state directly, and that property is allowing us to separate the mixtures. And we can also make use of magnetic attraction, where we are able to attract substances that are magnetic and separate them from non-magnetic substances. Let us first consider filtration. Here is our apparatus. We usually have a filter funnel. There is usually filter paper in the filter funnel, and we usually have a beaker to collect the liquid that passes through. The liquid that passes through the filter paper is a solvent and is known as a filtrate, and the particles that we're not able to pass through is known as a solid residue. Now, the principle is that this separates our large solute particles from suspension, so we filter suspensions. The important property that we have used to separate this mixture is the particle size. The particles of solutions and colloids would have been too small, and they would have been able to pass through the pores of the filter paper. So we do not try to filter a solution or a colloid, we usually filter suspensions. Next, we look at crystallization. In crystallization, we have a solution usually, or we could have even had even have a colloid. Now, in the case of crystallization, we have our solution. So we have the solvent and we have solute particles dissolved in it. What we do first is that we apply heat to our solution and we try to drive off the majority of our solvent. Once we have caused the majority of our solvent to evaporate, then we're going to have a lower volume of the solution with our solute inside of it. And we will take the container from the fire, we'll put it usually on the desk in the lab, and we allow the remaining solution to cool. And over time, we will see that crystals will start to form. This is useful because we get nicely formed crystals as the solution cools down. So for solutions or colloids that contain solutes that will not decompose on heating, crystallization is suitable. The solvent is slowly evaporated, allowing the crystals of the solute to be collected. The principle that we use in crystallization is that when we have the solution here, as we cool it down, the solubility of our solute decreases. So as it gets cooler, you will notice that more and more crystals will start coming out of this solution. For simple distillation, as we had discussed before, we can use this to separate a solution that has a solid dissolved in a solvent, a liquid solvent. But the difference between crystallization is that we wanted to collect the solute particles, the solid particles we were interested in. So we allowed the solvent to evaporate off. However, that is different. When we do simple distillation, we would have had the same solution, but our interest would have been to collect the solvent. We would have wanted the liquid solvent, and we were not so interested in the solid solute. So in simple distillation, we would have a flask, we'd have a heat source, we would clamp our flask, then we usually have a thermometer there as well, and then connected to our flask is a condenser. The condenser has some input ports that allow cold water to enter and the warm water to exit. But the water that is entering the condenser does not touch or vapor directly. It's just trying to create a cold or cool temperature that our vapor that was released here will actually be cooled and be condensed to a liquid so it can be collected here. So for simple distillation, we would have had a mixture, which could have been a mixture of two miscible liquids, or it could be a solution where we had a solid in a liquid, but we were interested in collecting the liquid. Or if we had two liquids here, we would have been able to separate the two liquids because they had large differences in their boiling point. So one liquid would be collected first, and the next liquid would be left back here in the flask. So the principle of simple distillation is that the solvent particles vaporize with heat and is then condensed back into the liquid state. If it was a solution, then the non-volatile solute would have stayed in the flask and the solvent would have been collected here. This technique is useful when collecting the solvent from a solution or colloid. It's also used for miscible liquids with a difference in boiling point of 50 degrees Celsius or more. In fractional distillation, as you can see, we have added a fractionating column, which is a tall column that is usually packed with beads to increase the surface area. And the purpose of the fractionating column is to separate the vapors that are going to arise from this mixture. So in the round bottom flask, we usually have a mixture of two miscible liquids. Once we start heating the flask, the liquid with the lower boiling point is going to turn into vapor first and start rising up. Then the next liquid is going to also turn into vapor. So you will find that both liquids would be converted to vapors, and the two vapors are going to come up here into the fractionating column. However, the purpose of the fractionating column is to allow one of the vapors to be slowed down. So usually the vapor of the liquid with the higher boiling point is going to be slowed by the fractionating column. And the one that has the lower boiling point is the vapor that will be allowed to rise faster. It will enter the condenser and it will turn into a liquid and be collected here as a distillate, and the liquid with the higher boiling point would remain in the round bottom flask. So the principle of the fact is that the fractionating column separates the vapors of a mixture of two miscible liquids with close boiling points. That is, they have a difference in their boiling points of less than 50 degrees Celsius. The column allows the vapor of the liquid with the lower boiling point to get to the top first. It is then condensed and collected as a liquid distillate. The liquid with the higher boiling point remains in the flask, and this would be suitable, for example, to separate ethanol and water mixture. This table allows us to compare fractional distillation to simple distillation. Fractional distillation is used to separate two or more liquids with close boiling points. Simple distillation is used to separate liquids with large boiling point differences. And fractional distillation uses a complex apparatus. With a fractionating column, simple distillation does not need a fractionating column. For fractional distillation, you usually have to repeat the process several times to get pure components. Simple distillation does not need to be repeated multiple times. Fractional distillation cannot be used to separate a solvent from a solute. It can only be used to separate two miscible liquids, but simple distillation can be used to separate two miscible liquids, and it can be used to separate a solute from a solvent. Fractional distillation is used in the refining of crude oil, and simple distillation is used to purify seawater, where we are more interested in collecting the water than we are in collecting the salt. This is showing us an example of fractional distillation of crude oil, and we get the various components of crude oil. So this is a large fractionating column. Now the separating funnel, as we see here, is a large glass apparatus that has a stopper at the bottom. Now when we put our two liquids inside our separating funnel and shake it together, the liquids are not miscible. They have large differences in their polarity. So one liquid will settle to the bottom while the other floats to the top. The one that floats to the top is the one that has a lower density. The one that goes to the bottom has a higher density. So the principle is that the two liquids have different polarities and they are immiscible. The liquid of lower density will float on top when the mixture is shaken. Now to separate them, you would open the top and collect one liquid. And then once this liquid is out, you will move the container and use another container to collect the second liquid afterwards. The separating funnel can be used in the process of solvent extraction, which is basically also known as a liquid-liquid extraction. And this method is used to separate compounds based on their solubilities in two different immiscible liquids. So usually you would have a solvent like water, and then you would have another solvent, an organic solvent, which is non-polar, and the water is polar. Now, if you had a mixture, some of the components of the mixture would prefer to dissolve in water because they are polar, just as water is polar. And then some components would prefer to dissolve in the organic solvent because the organic solvent is non-polar and they are non-polar. So if you should have water and an organic solvent together and shake with this mixture, then you will see that some components would prefer to go to the water and some would go to the organic solvent. Now, this apparatus is explaining solvent, or this diagram is showing us solvent extraction. Here we have a mixture that has two different types of particles. We add a second solvent to it, which is immiscible to this first solvent, and we shake it. We notice now that the black particles prefer to go in the top layer than the red particles. Red particles prefer to stay in the bottom layer. So this is a case where, because there are two different solutes, two different solvents with different polarities, we can basically cause these two components to be separated and go into the solvent that they prefer, the one that has a similar polarity to their polarity. And then we can pour out the bottom layer and we'll call it the red. We can get the red particles by doing crystallization or filtration, not filtration, sorry, crystallization or evaporation. And then we would collect the second layer here, which would have our black particles mostly, and then we could get out the particles by doing the same evaporation or crystallization. Then we have paper chromatography. Paper chromatography is a technique that is used to separate the components of a solution, and the components have very similar properties. However, they do have slight differences in their polarities. So the only difference that we have between the particles in a solution that we use paper chromatography to separate is that they have slightly different polarities, and we're going to make use of that difference in polarity. So the apparatus is usually set up with a strip of paper, a beaker that contains our solvent, which is known as our mobile phase. We also usually cover the beaker because we want the air around the beaker to become saturated with the vapors of our mobile phase or solvent. So the paper is our stationary phase and it is made up of cellulose. Now cellulose is polar. The mobile phase is usually a mixture of solvents that have a lower polarity than what cellulose has. So the cellulose is polar and the mobile phase is usually less polar. Now, the polar components in the mixture that we're trying to separate will be more attracted to the cellulose in the paper. And so they will not travel as far with the mobile phase as it moves up the paper. The spots that travel farther up the paper spend more of their time in the mobile phase. And since the mobile phase is less polar, it means that these spots were also not very polar. So they preferred to stay with the mobile phase and travel up the paper. And those that were very polar preferred to stay with the paper and didn't travel far. So spots that traveled short distances spent more time with the stationary phase. Again, we can see how the setup of the paper chromatography looks. So we would have had a chamber or a beaker. Then we would have had our paper that we usually put in the beaker. And then we have our solvent. We usually have a line that we draw in pencil. And then we put a spot of our dye or ink that we are trying to separate. When we put the paper into the container, we have to make sure that the liquid is at a lower level than the line that we drew. And then we will leave it, and then the water will slowly rise up the paper by the action of capillarity. As the water travels up the paper, it will separate the components of our ink or our dye. We will notice that if the ink was pure, it would have been only one spot that we see. But if our ink is impure, we will notice that it separates into various spots that travel to various distances. Now, as you can see here, we possibly had a dye here that separated into 3 spots, red, purple, blue. The blue spot traveled the furthest distance. It traveled approximately 8 centimeters. Now this blue spot traveled furthest because it was more close in polarity to the mobile phase. So it traveled with the mobile phase. It did not stick very strongly to the cellulose paper, as opposed to the red spot. The red spot only traveled 2 centimeters, which means that it spent more time attached to the cellulose, which is the stationary phase, than it spent in the mobile phase. Also notice that when the solvent rises up to about 1 centimeter away from the edge of the paper, we usually take out the paper out of the solvent and we mark a line in pencil known as the solvent front. This tells us where our solvent stopped. So we would have had our baseline, and then we have our solvent front, and we measure the distance between them. And that in this case is 10 centimeters, and that is the distance traveled by the solvent. We will use these values to calculate something known as our RF value. So our RF value, or our retention factor, tells us the distance traveled by a certain component divided by the distance traveled by the solvent. So in this case, our solvent traveled a distance of B, and this spot traveled a distance of A. So our RF value will be A divided by B. It usually does not have any units. Now, samples with spots that give us large RF values mean that they traveled very far with the mobile phase, and those that have low RF values mean that they did not travel very far and they stayed more with the stationary phase. Our final separation technique that I want to mention is centrifugation, which essentially can separate colloid mixture for us. And what it does is that we essentially put our mixture into the centrifuge that will rotate at very high speeds, and it uses the force of gravity to pull the solid particles, or heavy particles, to the bottom of the tube. Blood is an example of a colloid, and if you should spin blood in a centrifuge, you will notice that it separates into various components. We would have the solid particles of blood settling to the bottom, and then we have plasma to the top. So centrifugation is widely used in biological separation. And it is a technique in which solutes are separated by their different rates of sedimentation in a centrifugal field. Sedimentation rates of solutes is determined by their size, shape, and density, and the density and viscosity of the media. And there are low speed, high speed, and ultra centrifuges. I really do thank you for watching this module, and I'm asking you kindly to like, comment, and subscribe. And we will continue with our revision of the CXC syllabus for chemistry in our next module, Module 4. Thank you for watching.